Across the celestial sphere, within the star-dusted boundaries of the constellation Aquila, the Eagle, lies a point of light indistinguishable from its countless neighbors. It is catalogued, measured, and tracked by an unblinking eye in orbit around the Earth, the Gaia spacecraft, a surveyor of galactic motion on a scale previously unimaginable. This instrument does not seek marvels, it seeks data, charting the precise positions, velocities, and parallaxes of over 1 billion stars to construct a kinematic map of the Milky Way in 3 dimensions. In the silent torrent of telemetry, in the subtle shifts of light measured over months and years, an anomaly presented itself. A single, ancient star, a giant in its twilight years, was not moving as it should. It was tracing a slow, elegant, but distinctly perturbed path through space, exhibiting a gravitational wobble of profound implication. This star was dancing with a partner, an entity whose presence was betrayed by nothing more than its immense gravitational pull, a silent, invisible colossus exerting its influence from across a gulf of empty space. This unseen companion, designated Gaia BH3, was calculated to possess a mass some 33 times that of our own Sun, making it the most massive stellar mass black hole yet detected within our galaxy, a titan hiding in plain sight. The object itself is an expression of gravity in its most absolute and final form. It is not a place, but a condition of spacetime, a region where the fabric of the cosmos has been warped to its breaking point. At its heart lies a singularity, a point of theoretically infinite density where the known laws of physics cease to apply, the compressed remains of a star that was once unimaginably vast. Surrounding this point is the event horizon, a spherical boundary of no return, a one-way membrane separating our universe from the unknowable interior. For an object of 33 solar masses, this boundary, its Schwarzschild radius, would measure approximately 100 kilometers across, a sphere of perfect blackness smaller than many asteroids, yet containing the mass of a generation of stars. Unlike the supermassive black hole at our galactic core, Sagittarius A, which is 4 million times the Sun's mass and occasionally flares as it consumes interstellar gas and dust, Gaia BH3 is dormant. It is not actively accreting matter. There is no swirling, superheated disk of material spiraling into its grasp, no incandescent jets of energy being launched from its poles, no telltale flicker of high-energy X-rays to betray its location. It is gravitationally loud but electromagnetically silent, a pure manifestation of mass without light. Its existence is inferred only through the precise, clockwork motion of its companion, a lonely star orbiting a void, its trajectory a testament to the sheer weight of the darkness it encircles. This silence is what makes it so extraordinary. It is a member of a predicted but largely unseen population of black holes that drift through the galaxy as dark ghosts, their census only just beginning. Its sole companion, the star that acts as the system's only visible component, is a crucial witness to the black hole's history. It is an ancient, subgiant star, progressing through the later stages of its life, having exhausted the hydrogen fuel in its core. Spectroscopic analysis of its light reveals a chemical composition of profound significance. It is extraordinarily metal-poor. In astronomical terms, metals refer to any element heavier than hydrogen and helium. A low metallicity indicates that the star was formed in a much earlier cosmic epoch, from a cloud of primordial gas that had not yet been significantly enriched by the supernova explosions of previous stellar generations. This star is a relic, a survivor from the Milky Way's youth, or perhaps from somewhere else entirely. It orbits its dark companion in a wide, leisurely ellipse, completing a single circuit every 116 Earth years. This vast separation is critical. It suggests the binary system has lived a relatively undisturbed life, its orbital architecture not violently rearranged by the cataclysmic event that must have created the black hole. The star's ancient, unpolluted nature provides a pristine sample of the material from which both it and the black hole's progenitor were born. It is a time capsule, and its motion is the key that unlocks it. Every subtle dip and pull in its velocity, measured by the Doppler shift in its starlight, tells a story of the immense, invisible mass it is gravitationally bound to, a silent partner in a cosmic dance that has lasted for billions of years. To create a remnant as massive as Gaia BH3, the progenitor star must have been a true behemoth, an object of almost mythical proportions. Current models of stellar evolution suggest that to leave behind a 33 solar mass black hole, the original star must have begun its life with a mass well over 100 times that of our Sun. Such a star would have been an O-type giant, a luminous blue variable, burning with a ferocity that is difficult to comprehend. Its surface temperature would have exceeded 50,000 Kelvin, its luminosity millions of times greater than our own star, a brilliant, searing beacon in the primordial galaxy. But the life of such a massive star is violent and fleeting, a brief, incandescent existence lasting only a few million years. The primary challenge for such a star to form such a massive black hole is mass loss. Throughout their lives, massive stars generate powerful stellar winds, streams of charged particles that flow outward from their surfaces, driven by the intense radiation pressure from their cores. In stars rich in metals, like those forming in the modern Milky Way, these winds are extremely efficient, stripping away a significant fraction of the star's mass over its lifetime. A star that begins with 120 solar masses might shed more than half of its substance back into space before it dies, leaving a much smaller core to collapse. Here, the metal-poor nature of the system becomes the central clue. The progenitor of Gaia BH3, like its surviving companion, must have formed from metal-deficient gas. In such a star, the stellar winds are far weaker, less effective at pushing away the outer layers. Without a high abundance of heavy elements to absorb the photon's momentum, the star retains much more of its initial mass. It lives its short, brilliant life almost entirely intact, a gravitational giant hoarding its substance, preserving its mass for its final, inevitable collapse. The death of this colossal, metal-poor star was likely a far quieter and more profound event than the celestial fireworks typically associated with the end of a massive star's life. The standard model for the death of a star more than 8 times the mass of the Sun is a core-collapse supernova, a cataclysmic explosion that can briefly outshine an entire galaxy. In this process, the core implodes, but the resulting shockwave violently expels the star's outer layers into space, seeding the interstellar medium with newly forged heavy elements. While this is a common fate, it is also an inefficient way to form a massive black hole, as the explosion itself carries away the very mass needed to create a large remnant. The existence of a 33 solar mass black hole, especially in a wide binary system with an unpolluted companion, points strongly toward a different, more mysterious end: direct collapse. In this scenario, the star's core, upon exhausting its nuclear fuel, begins to implode under its own monumental gravity. But instead of generating a powerful, rebounding shockwave, the collapse is so overwhelming and so rapid that the entire star, from its core to its outermost layers, falls inward without halt. The escape velocity at its surface quickly exceeds the speed of light, and the star simply vanishes. There is no grand explosion, no supernova remnant, no expanding nebula of enriched gas. The star just winks out of existence, its light and substance swallowed by the event horizon it creates in its final moments. It is a silent, complete gravitational failure, an implosion so total that almost nothing of the progenitor star's vast mass is lost. It is not an explosion, but an extinguishment, a quiet transition from a brilliant point of light to a perfect patch of darkness. The forensic evidence for this silent, direct collapse is written in the very atmosphere of the surviving companion star. If the progenitor of Gaia BH3 had exploded in a conventional supernova, it would have blasted its surroundings with a wave of ejecta rich in heavy elements like oxygen, silicon, and iron, all forged in the final, fiery moments of nuclear fusion within its core. The companion star, orbiting nearby, would have inevitably passed through this cloud of debris, its own gravitational field capturing and incorporating some of this enriched material. Over time, its surface layers would have become polluted, its spectrum revealing the distinct chemical fingerprints of its deceased partner's explosive end. Yet, when astronomers analyzed the light from Gaia BH3's companion, they found no such contamination. Its atmosphere is remarkably clean, composed almost exclusively of the light elements hydrogen and helium, consistent with its ancient, metal-poor origins. It shows no signs of the elemental pollution that a supernova would have guaranteed. This, negative evidence, the absence of something that should be present, is an incredibly powerful clue. It tells a story not of what happened, but of what did not. The pristine nature of the companion star is a silent confirmation that the black hole's creation was not a violent, explosive event that showered the system with debris. It was a clean, contained collapse, a process that allowed the progenitor's mass to fall inward without contaminating its neighbor. The companion star orbits not just a black hole, but also the ghost of a star that died without a funeral pyre, its passing marked only by the sudden onset of an immense and silent gravity. Zooming out from the specifics of the binary system, its location within the Milky Way provides another layer of context, another piece of the puzzle of its origin. The Gaia BH3 system is not a resident of the galactic disk, the flattened, spiral-armed structure where our Sun and the majority of the galaxy's stars reside. Instead, it is found in the galactic halo, a vast, sparse, and roughly spherical region that surrounds the entire disk. The halo is populated by the galaxy's oldest objects, ancient stars, globular clusters, and a significant amount of dark matter. More telling than its location is its motion. The system is traveling on a retrograde orbit, moving in the opposite direction to the bulk rotation of the galactic disk. This is a telltale sign of an object that was not born within the Milky Way's primary star-forming plane but was instead accreted from outside. The most likely scenario is that Gaia BH3 and its companion were once part of a smaller satellite galaxy or a massive globular cluster that, billions of years ago, strayed too close to the nascent Milky Way. Our galaxy's powerful tidal forces would have ripped this smaller structure apart, its stars and dark matter being stretched into long stellar streams and eventually assimilated into the Milky Way's halo. Gaia BH3 is therefore an extragalactic immigrant, a relic from a long-devoured galaxy. This origin story neatly explains its metal-poor composition, as smaller dwarf galaxies often have a less vigorous history of star formation and chemical enrichment compared to large spirals like our own. The black hole is not just a remnant of a massive star, it is a remnant of a different galaxy, a silent monument to an act of galactic cannibalism that occurred in the deep past. The discovery of a 33 solar mass black hole, formed from a metal-poor star in the galactic halo, has profound implications for our understanding of stellar and galactic evolution. For decades, theoretical models suggested that forming such massive stellar mass black holes within the Milky Way should be exceedingly difficult, if not impossible. The metallicity of our galaxy's disk was thought to be too high, enforcing a mass limit on black hole remnants due to the powerful, mass-shedding stellar winds of metal-rich stars. Black holes in the range of 5 to 15 solar masses were expected and have been found, but an object over 30 solar masses was considered an outlier, perhaps only possible in the very early universe before heavy elements were widespread. Gaia BH3 challenges this paradigm directly. It provides the first concrete observational evidence that this formation channel, the direct collapse of a massive, metal-poor star, can and does occur. It serves as a local analog, a nearby example of the types of processes that must have been common in the early cosmos, which was universally metal-poor. This single object acts as a benchmark, a calibration point against which theories of massive star evolution can be tested and refined. Furthermore, it has implications for the origin of the supermassive black holes that sit at the centers of galaxies. One theory suggests they grew from smaller, seed, black holes, which may have been formed from the collapse of the very first generation of stars, the so-called population 3 stars, which were entirely metal-free. Gaia BH3, while not a population 3 remnant, is a crucial stepping stone, demonstrating that low metallicity is indeed the key to producing unusually massive stellar black holes, lending credence to the models of black hole growth in the early universe. The story of Gaia BH3 is also the story of the instrument that found it, a testament to a particular philosophy of scientific inquiry. The Gaia spacecraft was not designed to hunt for black holes. Its mission, elegant in its simplicity and staggering in its ambition, is to conduct a census. By repeatedly scanning the entire sky over many years, it measures the precise astrometric properties of stars, their positions, their motions across the sky, proper motion, and their distance from us, parallax, with a precision measured in microarcseconds, equivalent to measuring the diameter of a human hair from 2,000 kilometers away. From this exquisitely precise data, a dynamic, three-dimensional map of our galaxy is constructed. The discovery of Gaia BH3 was a serendipitous consequence of this methodical, unbiased survey. The wobble of its companion star was not something an astronomer specifically looked for at that location, it was an anomaly that emerged from the comprehensive dataset when analyzed for binary systems. This highlights a powerful truth in modern astronomy: discovery is often driven not by targeted searches for expected phenomena, but by the systematic and precise mapping of vast volumes of space. By simply measuring everything as accurately as possible, the universe reveals phenomena that were previously hidden or entirely unimagined. Gaia's gaze is patient and comprehensive. It treats every point of light as equally important, and in doing so, it uncovers the exceptions, the outliers, the systems that do not conform to our expectations. Gaia BH3 was hiding not in a shroud of gas or behind a veil of dust, but within the subtle gravitational cadence of its partner's orbit, a secret waiting for an instrument precise enough to hear its silent rhythm. Ultimately, we are left with a sense of the profound silence and hidden immensity of our own galaxy. Gaia BH3 is a dormant giant, a sleeping titan. For billions of years, it has drifted through the galactic halo, its existence entirely encoded in the gravitational field it projects into the surrounding space. It is a reminder that the most massive objects are not always the most luminous. The universe is not only what we see through light, but also what we feel through gravity. Theoretical calculations suggest that the Milky Way should contain tens of millions of stellar mass black holes, the graveyards of countless generations of massive stars. The vast majority of these, like Gaia BH3, will be dormant, not actively feeding and therefore invisible to our X-ray telescopes. They are a dark population, a hidden component of our galaxy's mass, their collective gravity subtly shaping the orbits of the stars we can see. The discovery of BH3 is likely just the beginning. It is the first confirmed member of a new class of object within our galaxy, the massive, dormant black hole. As analysis of the Gaia dataset continues, and as future observatories with even greater sensitivity come online, more of these silent companions will likely be found, their wobbling partners betraying their presence. The Laser Interferometer Space Antenna, LISA, a future space-based gravitational wave observatory, may even be able to detect the faint ripples in spacetime from such binary systems directly. We are slowly mapping the galactic underworld, charting the distribution of its dark remnants. Each new discovery, like that of Gaia BH3, does not just add a new object to our catalogs, it deepens our understanding of the cosmic cycles of birth, life, and death, and reveals the quiet, persistent, and overwhelmingly powerful presence of gravity, shaping a universe that is far vaster and more mysterious than what is revealed by light alone. The very existence of this system, a metal-poor giant star in a stable, long-period orbit around a massive black hole, is a statistical improbability that offers a window into cosmic history. The conditions required for its formation are exceptionally specific. First, a binary star system had to form from a pocket of primordial, metal-deficient gas. This in itself points to an origin in the early universe or within an accreted dwarf galaxy, where such pristine building blocks were more common. Second, one of the stars in this pair had to be exceptionally massive, while its companion was of a more modest, longer-lived variety. Third, the initial orbit had to be wide enough so that the two stars evolved largely independently, without significant mass transfer between them, which could have dramatically altered their evolutionary paths. Had they been closer, the massive primary star would have swelled into a red supergiant and its outer layers would have been siphoned off by the companion, preventing the formation of such a large black hole. The wide 116-year orbit we see today is likely a relic of this initial separation, preserved through the final collapse. Fourth, and perhaps most critically, the massive star had to retain its mass and then collapse directly, avoiding a supernova that could have disrupted the binary system entirely. A powerful supernova kick could have easily ejected the companion star, leaving behind an isolated black hole, or dramatically altered the orbit into a much more eccentric path. The stable, nearly circular orbit of the companion is a strong indicator that the system remained gravitationally bound and relatively undisturbed during the black hole's birth. The confluence of these factors, the right environment, the right initial masses, the right orbital separation, and the right mode of stellar death, makes the Gaia BH3 system an exquisite cosmic fossil, preserving a perfect record of a rare and ancient formation pathway. Contemplating the scale of time involved deepens the sense of awe. The companion star, with its low mass and ancient composition, has likely been shining for over 10 billion years. For the first few million years of its existence, it shared its orbit with a brilliant, blue-white giant, a star that dominated their corner of space. Then, in an instant of geological time, that brilliant neighbor vanished, replaced by an invisible nexus of gravity. For the subsequent billions of years, for a span of time encompassing the entire history of our own solar system and the evolution of life on Earth, this star has continued its lonely, silent orbit around the void left behind. It has circled this patch of darkness hundreds of millions of times, its path dictated by the ghost of its long-dead partner. This immense temporal landscape highlights the stability and persistence of gravitational systems. While stars burn out and cosmic structures evolve, the laws of orbital mechanics are patient and unending. The companion star serves as a celestial clock, its laps around the black hole marking the passage of eons. It is a living artifact from a time when the Milky Way was still assembling itself, and its continued, steady motion is a quiet affirmation of the enduring power of mass to shape the cosmos across the deepest gulfs of time. Observing it is akin to watching a geological process, but one played out on a stellar stage, where the forces are gravitational and the timescale is the age of the galaxy itself. The physical properties of the black hole itself invite further contemplation on the nature of matter and energy. Inside its event horizon, 33 times the mass of the Sun is compressed into a region of zero volume. This mass did not disappear, it is still there, exerting the same gravitational force it did when it was a star. It is a repository of conserved information, mass, charge, and angular momentum, but all other details of the progenitor star have been erased. The complex layers of fusing elements, the turbulent convection cells, the magnetic fields, the vibrant photosphere, all have been homogenized into the three simple properties that define a black hole. This process of collapse represents a fundamental transition in the state of matter, a conversion of complex baryonic substance into pure spacetime curvature. The black hole is, in a sense, the ultimate form of storage, where the universe archives mass in its most compact and efficient form. The dormancy of Gaia BH3 means this mass is currently sequestered, locked away from the rest of the cosmos. Were a star or a gas cloud to stray too close, this stored potential would be unleashed. The infalling matter would form an accretion disk, and the gravitational potential energy of the mass would be converted into unimaginable heat and light, turning the dark object into one of the brightest X-ray sources in the sky. For now, however, it remains in a state of pure potential, a quiet engine of gravity waiting for fuel. Its presence is a subtle but constant reminder that the universe is filled with such reservoirs of latent power, their influence felt only through the patient, inexorable pull of their mass. The discovery also casts a new light on the search for other forms of cosmic darkness, particularly dark matter. While black holes like Gaia BH3 are made of ordinary, baryonic matter, the same protons and neutrons that constitute stars and planets, their invisibility makes them a component of the dark universe. For a time, it was hypothesized that a significant fraction of the universe's missing mass, attributed to dark matter, could be composed of primordial black holes formed in the Big Bang. While extensive searches have largely ruled out this possibility for most mass ranges, the existence of a large population of dormant stellar mass black holes, as hinted at by Gaia BH3, means that our census of the galaxy's baryonic mass budget is still incomplete. These objects, while not the solution to the grand dark matter problem, represent a non-luminous mass component that must be accounted for in detailed models of galactic dynamics. By finding more of these systems, astronomers can better estimate their total number and mass distribution throughout the galaxy, particularly in the halo. This will lead to a more accurate picture of the Milky Way's total mass and structure, helping to disentangle the gravitational effects of baryonic matter, stars, gas, and black holes, from those of the still elusive non-baryonic dark matter. Gaia BH3 is therefore not just a curiosity, it is a new tool, a new type of gravitational probe for weighing the galaxy and understanding its most massive and mysterious components. Finally, the narrative of Gaia BH3 returns us to our own perspective, to the act of observation and the nature of knowledge. This colossal object, which has existed for billions of years, only entered our reality, our sphere of understanding, in the last few years. It existed independently of our awareness, following the laws of physics in the cold darkness of the galactic halo. Its discovery was not an invention, but an uncovering, a moment when our technological senses became sharp enough to perceive a reality that was always there. It speaks to the limits of our perception and the vastness of our ignorance. For every cosmic marvel we uncover, there are countless more that remain beyond our current ability to detect. The universe is not empty, it is merely dark to our limited senses. The story of Gaia BH3 is a lesson in humility. It suggests that our catalogs of the cosmos are profoundly incomplete and that our most fundamental models are always subject to revision by a single, inconvenient observation. It encourages a mode of exploration that is patient, methodical, and open to surprise. The most significant discoveries may not come from searching for what we expect to find, but from building instruments capable of seeing the universe in a new way, with greater clarity and precision, and then listening carefully to the subtle, unexpected stories the data tells us. The wobble of a single, distant star, measured with astonishing accuracy, has revealed a hidden giant and rewritten a chapter in the story of how stars die and how galaxies are built. It is a quiet testament to the power of looking closely, and a promise of the further wonders that still await us in the silent, gravitational dark.